Okay, so I'm going to go over the worksheets first. For complexity, you have a quiz that's due on Tuesday. Don't forget you have a quiz that, no, assignment due, I think it's Sunday, I guess. I know the 28th, I think. But I could be wrong. Just check the assignments on Canvas. Let's see, I had a problem sharing the screen before. And let's see here. Yes, here it is. And I posted this online and I put the solutions too. So this is something we talked about last time, how to get estimate the runtime for just kind of a simple loop, the kind of loops that we do in math, like 130. Okay, so the important thing to notice is here, I actually wrote the solution here. Well, I have the solution there already, but here, okay, so I'll put it back in. Okay, so first of all, notice that in all these loops, there's a constant number of iterations or constant number of operations per iteration. And that's actually a critical feature. If the number of operations in an iteration was a function of like the counter variable, then we couldn't do what I'm about to do. Okay, so like in that first one, part A, in all of them, it's just one addition. So it doesn't matter if it's 1 or 3 or even a million. The fact is that it's a constant, but if it varied based on the value of the counter variable, something else, then this analysis wouldn't hold. Okay. So given that, fact, all we have to do is then look at the counter variable. How's the counter variable changing? Is it a geometric sequence or arithmetic? So geometric, I mean that the counter variable is either being multiplied or divided by a constant. Well, dividing is the same as like multiplying, like they were multiplying by 1/3. And arithmetic would mean that we're adding or subtracting a constant. Okay, so if the counter variable changes geometrically, like here, let's say in that case, n, let's say n was 243, so it would go down like powers of, so like here. So if n is, so it's about log base 3 of n. So then so the m would be 243, and then 81, and then 9, and then 3, and then eventually 1. And then when it gets to 0, it stops. Okay, so, okay, is that, oh no, I missed 127, sorry. 81 divided by 3 is 27. Okay, so you see that that 243 is 3 to the 5th power. So basically, it's log of n. The number of iterations is actually log of n plus 1, because it's actually, well, actually we actually go down to m equals 0. I'm sorry, because we have to look at the value of m where it fails. So it's about log of log base 3. So that's the number of iterations. Okay, but it may be off by 1. Okay, so these loops where the counter variable changes geometrically, it's just log of n. So we would just, so here, and it's just one loop. It's not a nested loop or anything. So it's just log of n. Give or take maybe 1 or 2 iterations, but that log of n gives a really very good estimate. Okay, so then so let's just look at the next one then. Okay, so again, so a is, all I have to do is see is that m is divided by m/3 to get to the next value of the counter variable. So I know that it's log of n. Now let's look at b. Okay, once again, first let's make sure that the number of operations per iteration is a constant, which it is. Oh, but look at this one. There's no value of n. So if you look at b, it's exactly, well, it's going to be 19 iterations, but it's going to fail when m is equal to 20. But there's 19 iterations here. And then we evaluate m equal to 20. But notice, it's a constant number of iterations. It has nothing to do with n. I could actually count the number of iterations. So it's going to be 9. So sum is 0, that's 1. And then we initialize m equal to 1 time. We do 20 comparisons. is n less than 20, so that's 22. We're going to increase m by 1 like 19 times, and some we're going to increase by 1 19 times. I can actually count the number of operations. It's exact. All right, so this is 1, this is 1 plus 19 plus 1. So when we compare m equal to 20, it's 1. We increase m 19 by 1 19 times. And so I said there's 19 iterations. So this is also 19 summation. So you add them together, you get a, what is it, 60 or something like that? Yeah, I think it's 60. Okay, so, but it's constant. Okay, so the answer for B is, and we'd actually write the answer as order 1. And here I'd actually write the answer. It's actually in my solution file. Here the answer is order log of n. Okay, but again, so the loop, the counter variable has nothing to do with n. We just say, well, it's a constant number of operations. So I don't care how big that, m is less than 20. I don't care if it's m less than a trillion. It's still a constant. It's not a function of n. So the number of operations is not growing as a function of n. It's a constant. Okay, so now let's look at part C. Okay, so now let's look at the counter variable, and now that's arithmetic, right? To get to the next value of m, so like m starts at 1, m is equal to 1, and then you keep adding 11, 12, 23, 34, 45. Okay, so the difference between any two consecutive values of m, we can always get the next value of m by adding by 11. That's what makes it arithmetic. You get the next value in the sequence by adding a constant, where geometric, you get the next value in the sequence by either multiplying or dividing by a constant. So in this case, so the number of iterations is about n over 11. Whoops, that's not helping. Let's just put it up higher. Okay, so remember when we write the big O notation, we drop the constant. All we care about is it's growing like n, some multiple of n. So we'll just say, so that's what this big O means. O of n means that the number of operation grows like a multiple of n. So we double the data size, we about double the number of operations required. Okay, so here's okay, so students, now we're getting to the really fun problems. D, E, F. Okay, so we have nested loop inside of a nested loop. Yeah, lots of nested loops there. But so we go, oh my God, this looks too hard. But no, it's not, students. Okay, so once again, look what actually is going inside the loop, and we're just adding sum by 1. So every iteration is a constant number of iterations. All we actually have to look at is how the counter variable is changing, geometric or arithmetic. So here, that's geometric. So this is log of n, about log of n iterations. This would be about n divided by 5. I don't really care because we're starting at n and then we're going every 5th one. Here we're just increasing by n, so this would be about n. Here I'm just gonna, so this first one would be like log base. I don't care about the base, but if I was going to put the best base would probably be log base 7. But remember, every base we can always convert from one base to another by multiplying by a constant. And so here this would also be log of n. And once again, if I was going to use a base, I'd put 5 there. But we can multiply. We can easily convert from log 5 to log 7 just by multiplying by a constant. Okay, so so now we just multiply these all together to get the approximate number of iterations. But remember, when we write the order of growth, and we write that big O notation, we drop all the constants so that we wouldn't have, we just drop that, see that n over 5 and right here, we would drop that quotient, the divisor of 5. So it's n squared, so it's n squared log n squared. So n2, and I'll put the subscript in. Okay, so students, make sure, okay, so warning, so notice that log of n, and if you put the subscript here, that's actually wrong. This is actually equal to, if you probably remember from whatever, algebra or calculus, right? In that case, we're taking log of the quantity n squared. In that case, so log turns exponentiation into multiplication. So we're that log of, so we're like this expression log, and you put the exponent goes over the g. That's just, mathematicians use that a lot to express, this is just log of n. Okay, so we're not taking log of n times n. So this is correct, right? What I'm about to highlight. So this is good. It's highlighted in this, I don't know, how about this really nice blue? Okay, so this is bad, not correct. I do see this sometimes, so let's use good notation. Okay, so let's do E now, and then it's the same thing. We'll just count, okay, so I kind of scroll down here because of all this typing. Okay, so we're going to do the same thing, and then we're going to look at, constant number of operations per iteration. And once again, we look at the counter variable. So here we got n. Here we have log of n. And there we have log of n. We just multiply them together. So it's the answer is order, and it's n, and then log, the superscript in. One thing you noticed is that somewhere, there's we have 4 loops where the counter, that are, the number of iterations is a function of n, like here for G. So somewhere, if you add up the exponents, it better be 4 because we have 4 loops there. And like here, is that the first one we actually, yeah. So here we have 3 loops where each loop is the number of iterations is a function of n. So if you add up the exponents, like n alone is n to the first, you add up the exponents, you should get 3. Okay, now this f is different. Okay, so notice, okay, once again, the number of operations per iteration is a constant. Okay, the outer loop, the number of iterations depends on n. So I'm just going to put an n here. This is, in fact, this would be like n iterations. But what about this middle one, the inner one? It has nothing to do with n. It's just a constant. It's always 10. We're going from, we start at k equal to 10, and it fails when k equals 0. So there's actually 10 iterations. But we compare k greater than 0 11 times, because we eventually compare 0 greater than 0, which is false. So this is just constant. I'm just going to put constant here. I'm not going to count. Okay, so if you multiply that together, you get some constant times n, but remember, we just dropped the constant. We were talking about the big O notation. And the answer is big O of n for the last one, even though it's a nested loop. But the inner loop just iterates. It's not a function of n. It's a constant number of operations. Okay, so I guess I'll continue. Add the values stored at the odd number indices of an array with n elements. Well, here we're just looking at. Here we're just looking at what? I think it's basically n over 2. So here the index would be like 1, 3, 5, 7. Right. So the answer is about. So it's about n over sorry, n over 2 additions. So the answer is, again, we drop the constant, so we just put order n. And oh no, oh students, this looks like a fun problem, H. So students, notice that this has nothing to do with the length of the array. We're just adding the first 3 values. I don't care how big that, you know, I'm assuming there's at least 3 values in the array. Okay, because that would be a problem. But if the array is a size 1 million or size 100, or, you know, it doesn't really matter. It's just 2 additions when you add the first 3 values. So it's so the answer is you know, but basically there's 2 additions. And so the answer is order 1. So when it's a constant, we just say order 1. We don't, even though it's 2 additions, we don't say order 2. That would look funny. So let's just use the right notation. And the answer is order 1. Okay, so now here, part 2. So we have these expressions, like these functions, and we want the big O notation. So we're just going to use these rules that we've learned. And you just use the highest order term. So be careful here. They may not be in what they call standard form, but here they actually are. So the first one's kind of not too bad. It's just, this is the highest order term. Order n squared. So it grows like n squared. So you double n, the number of operations grows by a factor of 4. And here, I don't know why Microsoft does this to me when I copy and paste. Okay, but let's see here if we can see. Okay, the highest order term is n to the 4th. What do they want here? Okay, that wasn't it. Okay. Okay, well, anyway, I'm just gonna, Microsoft has this context menu up there. I'm not quite sure what it wants. Okay, so for B, the highest order term is n to the 4th. So, oh, this didn't even make it do that. Okay, so let's just copy this here, and then the exponent. Oh, so all we care about, we drop all the lower order terms, and the highest order term is n to the 4th. So it grows like n to the 4th. So for really large n to the 4th is a lot bigger than n cubed. I mean, it's even at n 1,000, right? Because a million cubed, I mean, a million times, yeah, so if you had a million times, like 1,000 cubed is what, a million? Yes, 1,000 squared is a million, sorry. 1,000 squared is a million, and then you cube that, you get a trillion, and then you so 1,000 cubed is a trillion, and then you multiply that by 1,000, you get, what is after a trillion? I don't know. Anyway, but you see, when you multiply by 10 to the 3rd power, it's a big difference, right? Okay, so the dominant term there for a large n is n to the 4th. For small n, yeah, n cubed, and n might make it, a significant contribution. But as we start getting up there, even n equals 1,000, these lower order terms really are small compared to like n to the 4th. But it's unlikely we're going to use an algorithm that grows like n to the 4th. Okay, so C. So here, if you remember how, I don't have a graph, like a way to graph that, but for large, what do we know about 2 over n? For large n, as n gets big, 2 over n gets as close to 0 as we want. So if you actually graph that function, it would have an asymptote of y equal to 1. It gets closer and closer to 1. Right, so the bigger the n is, the closer that function 1 plus 2 over n gets to 1. So so here the order, so the dominant term is 1. So so first of all, 2 over n goes to 0 as n goes to I'm just going to write out infinity, so I don't have to. I'd have to go up there in the menu, look for the symbol. Okay, that's what we care about. 2 over n is really is insignificant for large n. Even for like n equal to 100, we have 0.002. No, 0.02, but n equal 1,000, which is really a very small data size, it's 0.002, which is, and 10,000, you know, so it's even for relatively small, what I would consider small values of n, 2 over n is really insignificant. So the answer is order. So in this case, because the n is in the denominator, the answer is order 1. Whoop, whoop, whoop. It's 1 is the dominant term. And the same thing here for D. I'm not, you just multiply that out, and you get all the terms will be, first of all, each individual factor goes to 1 as n goes to 0, as n goes to infinity. But if you actually multiply this out, you know, used a distribution, all the terms, you'd have 1 plus a bunch of terms where n is in the denominator. So this is also, I'm not going to do this. This is just algebra. Okay. Okay, so this last one, n log of n plus n. So because we're multiplying n by log of n, it grows faster. That's the dominant term. So, so let's say it's log base 2. So like for n equal to 1,000, the first term would be, you know, 10 times n, where the other one would just be just n. So that log function, it grows slowly, but it can get as big as you want it to be. So as n gets big, n log n dominates, is the dominant term. So it's just order n log n. Oops. And okay, so this binary search, okay, here, so I'm just going to stop sharing here just for a second and maybe see if I can cut and paste something from my other slide here, from the PowerPoint slide. So this is actually in Zybook, and I think it's in one of my PowerPoint slides. So here, let me just stop sharing here. And so let's see here. So let me just share this. Let's see. This is a PowerPoint slide, so I don't think it's not going to like it if I cut and paste. But let's go down here. We talked about this last time, and this is actually straight out of the book. This, yeah, I don't know whether I can copy this. Let's try this. And then if not, I might open up the have to look for the PowerPoint slides and not the PDF file. Okay, so let's go, let me see something here. Oh, that kind of worked. Okay, so here, I'm going to share this again with you in a minute. Okay, so so let me go back to the Word file with the problems in it. Okay, so that looks kind of small there. I took that out of it's actually that the complexity, I think lecture 2. Here, I can maybe make it a little bit bigger. And it's not formatted. This is straight out of Zybooks too. So this is the pseudocode. Notice that this is not real Java code. This is actually a pseudocode. And so this next problem is going to basically use this pseudocode. So remember, binary search is, it allows us to, we're looking for a value or key inside a set of an ordered list. So the numbers in this case is an array of integers, and it has to be sorted in ascending order. And if it's not, it doesn't work. Okay, so so let's just see if we can at least do one. I might just do one of these problems. Okay, so okay, so we have this list. There's actually 13 values in it. 209 is at index 12. And we're looking for 200. Okay, it says, what is the first middle element that is compared against 200? So remember the middle, we just take the average of, so the low and the high in this case, I'll even type out, even though it's not, we're not asking for that. So low is that first number, Then basically, the first time we call binary search, low is 0 and high is length minus 1. And it's it's 12. And then mid is equal just to the average of the two. Okay, so numbers of 6, so looking at numbers of 6 is equal to 61, I believe. Okay, right. Okay, so now, so what will the low and high argument values be for the first recursive call? Now we're looking for 200. Okay, so 200 is greater than 61. So 200 is greater than 61. See if I can highlight all of that. Okay, so 200 is, so since it's sorted, if 200 is greater than 61, the middle element, it's greater than everything to the left of 61. So we don't have to consider what's to the left of 61. We only care about what's to the right. So if 200 is in this list, it has to be on the right side of 61. So we look so the high doesn't change, but the low is directly 1 to the right of mid. Okay, so in this case, low, in this case, is mid plus 1, which is 6 plus 1, which is 7. And then the high doesn't change. The only thing that's going to, it's either the high that changes or the low that changes, but definitely not both. Okay, so the next time you call binary search, the low will be 7 and the high will be 12. Okay, and I'm actually going to show all the calls here. So I'm going to, and I think it's actually 4. This thing goes, first of all, the number of comparisons is about log of n, log base 2 of n, and the list is small, so it's about, it can't be really any more than 4 because it's, it's not greater than, it's somewhere between 8 and 16. So, okay, so, and I think the answer is 4. So let's just look. So the first time we call, your quiz kind of is like this. So that's 1. So in this case, so low is equal to 0. Right to this mid is equal to 6. And we know that numbers of 6 is less than 200. Okay, so we go to the right. So in this case, yeah, so we go, so the next time we call binary search, it's the low that changes. So and it's 1 more than mid. Okay, so now the low is 7, the high is 12, and the mid is and that's 19 divided by 2, so that's 9. And then, okay, so what's at position 9? And I think it's 109. Okay, so numbers of 9, which is 109, is less than 200. Okay, so 200 is greater than 109, which means that 200 is greater than everything from 7 to 9. There's no reason to look anymore because the second time we call binary search, we're only considering, we're just considering elements from 7 to 12. Okay, but we know that 200 is greater than what's in position 9. So it's got to be greater than what's in position 8 and 7 because it's sorted in ascending order. So let's stop looking stop looking at position 7, 8, and 9. So the next time we call binary search, we look at low changes again, and it's 1 more than mid. So there's our third time calling. So 1 more than mid is 10. So now we're going to look from 10 to 12. Your low is 10. Your high is 12. Your mid is 12 plus 10 divided by 2, which is 11. that right? 22, hopefully I did this right. And yeah, so it's 11. And then 200. So the next time we call binary search, what happens is, okay, so, oh, the mid was, okay, so let me see. So, oh, I think I made it. Hold on here, students. Did I make a mistake here? Okay, so the mid is, so maybe it's 3 calls here. So let me see here. Okay, so 7, yes, so let's see here. Okay, so number, yes, 0 to 12. Yeah, the mid was 6. Okay, so then we call numbers 7 to 12. Okay, so then, yeah, so we look at numbers of 9. Numbers of 9 is 109, and that's less than 200. Yeah, so the next time we call, oh, okay, so the next time we call it, yeah, so it's, yeah, so the low is 10 and the high is 12, which means that the mid is 11, and it turns out numbers of 11 is 200. Is that right? They're like, oh, no, numbers of 11, no wonder. No, numbers of 11 is 203. Okay, that's where I was getting confused. Sorry, students. I thought there were 4 calls. I know what's going on here. Okay, okay. So numbers of 11 is 203. Okay, so students. So in this case, so 203 is greater than. Okay, so let's see here. So what do we have here? So so in this case, what do we have here? We have 200. 200 is less than 203. Okay, so 200 is less than 203, so it's less than everything to the right of 203. So it's less than everything to the right of 203, which means we don't have to, so we don't have to look in positions 11 or 12. So the high changes. Okay, so now the low is going to stay 10, but the high is going to become 1 less than the mid. Okay, so the next to the very last time we call binary search. It's the low that changes. It's the high that changes. Okay, so in this case, because 200 is less than numbers of mid, which is equal to 203. Okay, so we look, the high will become 1 to the left of mid. Okay, so the mid was 11. Okay, so the high now becomes 10. And so now we just, obviously the mid is 10 because the average. And numbers of 10 is 200. So we found that, excuse me, students. Okay. Okay, so good thing I'm by myself. Okay, so, okay, so numbers of 10. So then you return 10. Let me just go, I think there's a little clunky. So let me just quickly go through this one more time. So the original problem, we're just looking through positions. We started initially, your low is 0, and the high is always the length minus 1, which is 12. And we're looking for 200. So we take mid is always the average of the low and the high. In this case, the mid is 6. So numbers of 6 is less than 200. So 200 is greater than everything to the left of 6. So your mid, so the low will become 1 more. So your mid will become 1 more than the low. So now the low will become 1 more than the mid. So now we move the low to 7. So we're gonna look only to values to the right of 6. So now we're gonna look from 7 to 12. Okay, we take the average of that, we get 9. So once again, numbers of 9 is 109. 109 is less than 200. So everything to the left of 9 is less than 200. So now let's just look at positions 10 through 12, right? So now your low becomes 10. So look at everything 10 through 12. So the only possible place it could be at this point is 10 through 12. When we get down to this third iteration, okay, so this is where I kind of, because I was looking at the wrong place. I thought 200 is at position 11. It's actually at 203. Okay, so now, okay, so we take the average of 10 and 12, and we get 11. And it turns out numbers of 11 is 203. So now your 200, the key that we're looking for is less than 203. So there's no reason to look to the right of 203. We'll only look to the left of mid. Okay, so your low is 10, and now the one directly less than 11 is 10. So now both the low and the very last call number 4, the low and the high are 10. So now obviously the average is 10, and luckily numbers of 10 is 200. And if that actually failed, what it would turn out is that you would return -1. Okay, okay, so but in this case, because we found the value we actually return the index. So you would return 10. Okay, and so I am actually not going to do another one of these. So actually, I have the answer sheet up. So I'm not sure if what my talking through is making it more confusing or not. But okay, hopefully that helped. Okay, so I'm going to stop sharing here. So this is it for the worksheet. Okay, so there's one more thing I wanted to talk about. So this is actually not on your quiz. Just kind of we'll talk about this more hopefully as the semester goes on. But it's that last section. So it's section I think 2.9 in the Xi book, and it's analyzing recursive algorithm, getting the big O notation. And so so let's see here. So of course I did not put up the slides here. So here, let me just, yes, this. Okay, here. So let me share again. Okay, so I'm just going to say some brief things about this. So it can get a little, just listening to me talk and be this, it's very abstract. So I don't know if it can get tedious listening to, or it's not like, it's not like sorting where I'm not actually kind of describing a recipe. Like binary search is a recipe. If you follow the instructions, you're guaranteed to get the answer every time. But it's like first, let's go to the left, go to the right. This is for people who really like math. So, so first of all, what is a recurrence relation? So it's some kind of function that can be defined in terms of the same function and a value less than n. And so there I gave 3 examples of recursive relationships or relations. So like the first one, f of n is equal to 3 plus f of n over 4. Yeah, so you see on the right, we see f on both sides, but on the right side, the argument passed to the function is less than the argument passed on the left side. N over 4 is less than n. So we're reducing it. So you can keep it, so you can expand that. So like f of n over 4 is 3 plus f of n over 16. And so you can actually expand these and then eventually try to get an expression, solve for f of n. Okay, so that's what I'm going to talk about right now. So I'm going to just solve for this recurrence relationship. And basically, when you get down to 1, it's 0 or like 1, or it's basically we can consider it 0 or 1 because there's only one element left in the data set, so there's really nothing to do. Okay, so remember, here's our recurrence relation, n plus f of n minus 1. So that was number 2? It was number 2. And we just keep expanding this. Well, f of n minus 1 is n minus 1 plus f of n minus 2. And we keep expanding that, right? F of n minus 2 is n minus 2 plus f of n minus 3. And eventually what you get down to is that summation, n plus n minus 1 plus n minus 2. And for those of you who have had calculus, I don't know if you learned this in kind of the pre-calc and algebra, there's that famous formula, 1 plus 2, the sum of the first n integers, the sum of the first n positive integers is n times n plus 1 over 2. So that's actually an exact answer. And so in this case, the order, if we were looking at, the order, the big O notation, how would we represent that function with the big O notation? We would just say order n squared, or big O of n squared. So this function grows like n squared. It's a second degree polynomial. Okay, so students, well, let's use recurrence relations let's see if we can get the complexity of our friend, the binary search algorithm. Okay, so one thing is that it's important to know is that every iteration of binary search is It's the same number of operations. I don't, I can remember that problem we just did. We had 4 levels of binary search, and every one you calculate, you first you compare the high and the low to see if you're done. So if low is greater than high, we're done. That's our base case, low greater than high, that means just get out. And then you compute the mid, and assuming that you haven't left, you compute the mid, you compare array of mid to the key, and if you haven't found the key, you call binary search again. So it gives an upper bound on the number of operations, but it's a constant. Is it like 5 or 6 or something? So that's important to know, that every time we call binary search, it's a finite number of operations. It has nothing to do with the length of the array. The length of the array, every time we call binary search, is irrelevant. Okay, and so what does each recursive call do to binary search? It reduces the part of the array that under consideration in half. And that's what we did in those problems. Like, so if the element that we're searching for is greater than like ARR of mid, we stop looking to the left of mid. And if the key that we're looking for is less than, array of mid, then we're done with the right side of the array. So each time we call binary search, the number of elements under consideration is being cut in half. And so this is how we get this recurrence relation. Okay, so let T of n represent the number of operations for binary search. Well, it's equal to K for every iteration. For every call, there's a constant number of computations. Let me say that again. So binary search at any level, the number of operations is a constant K plus, and then we call binary search again, only we cut the number of elements under consideration in half. And K just represents some positive constant. We don't really care what that is. So I think like for binary search, it's 5 or 6. But it doesn't even care if it's a million, right? It's just it's the same every time. It's not a function of the of n. And so we just keep it so T of n is K plus n over 2. And then, I left the PI, I have to correct it. Tree participant, yeah, if you go to tree participation activity 2.94, yeah, I realized I left the P out. Yeah, so there should be a P, I'll fix that. And then, and so they talk about this. And then it's, so it's K plus K. So anyway, we replace T of n over 2 with K, only now n over 2 is being divided by 2, and we get n over 4. Oh, now let's replace n over 4 with K, and we have to divide n over 4 by 2, we get n over 8. Eventually, what we're going to get to is T of 1, which is basically nothing, because when the data size is 1, there's nothing to do. So what do we get? We get K, we get this constant K plus K plus K, and we get it log over n, log of n times. The best base is 2. So again, all bases are log base n of 2 is equal to, we can easily convert that to any other base by multiplying by a constant. Okay, and so when you're dividing it by 2, you're dividing n by 2, it's about log of n divisions. So there's about log of n levels before we get to a level of the size 1. So first we're considering an array of length n, then length n over 2, and then n over 4, and then n over 2, and eventually that goes down to 1. And the number of and the number of levels is about log of n. Okay. Okay, so when we talk about big O notation, we don't care about the constant, right? We just drop the constant. Okay, so the big O representation for binary search is order log of n. It's pretty exciting. Okay. So let's just look at maybe one more example, and I think this is factorial. So we can represent factorial by this. So factorial is one operation per iteration, right? One multiplication, and then we have to call, then we call the same function and we pass it n minus 1. So this recursive relation, T of n, is equal to 1 plus T of n minus 1. That basically represents something like factorial. So this is actually kind of a bad recursive algorithm. If just reducing the data size by 1 is really not that helpful. Okay, so, for the most part, we don't compute factorial with recursive functions. It's just a really great example. again, if you keep doing this, eventually you're going to get to like T of 1, and the data size is 1. There's really nothing to do. So, the order of operations is about 0. And so what happens is that it's 1 plus 1 plus 1 n times. Okay, so T of n is essentially n, and the big O notation is order n. So the factorial recursive algorithm is about order n, and we knew that already. It's actually n minus 1 multiplication, but we say order n. It grows like n. Is there anything else? Okay, so here's one. There's something called merge sort. We haven't talked about in a few weeks. We're going to do, yeah, we're about to start sorting. Okay, so in fact, I will start that on Monday. Okay, so let's look at. So here's the recurrence relationship for this algorithm we haven't seen yet. T of n is equal to n operations, and then plus, and then it's T over n twice. We apply the algorithm to the left side and to the right side. Okay, so this gets to be a little bit of a mess when we actually write this out. And then, okay, so like T of n over 2 is n over 2 plus T of n over 4 plus T of n over 4. And we do that twice. And if we add it all up, so we're starting to reduce this. So the first time we see that, so the original definition is T of n is n plus T of n over 2 plus T of n over 2. And you expand it one time, you end up getting 2n plus 4 times T of n over 4. So it gets to be a little bit of a mess. And we're dividing by 2. So the number of levels is about log of n. And I think, I have another mistake. So this third, I'm going to just notice this level right here should have 4 n's in it. Okay, so yeah, sorry about that. So I'll fix that. And then, but basically, when you get down to T of 1, you get n log of n times. So the big O notation for merge sort, which we'll talk about eventually, is n order n log of n. And so I know that's a kind of a little bit. It's so far. I did put a Zodbook assignment. There's a few problems, and I'm going to try to find some more. It's kind of hard to find this. There's only a few problems, and so if you've seen it once, it's not too. If you've seen the problem, it's really. I can just vary that, vary the numbers a little bit, but there's really not too much critical thinking there. So I am going to. So students, if you have questions about the assignment, which I think is due on Sunday, just write me. And I'm going to stop this and eventually post this. And I'm going to make corrections to the PowerPoint slide that